All right, let's go.
Number 12. Volcanic activity on Io, a moon that should be dead but isn't. Before Voyager 1 arrived at Jupiter in 1979, scientists expected its moon Io to look something like our moon, cratered, dead, geologically inert. What Voyager found was the most volcanically active body in the entire solar system. Io has hundreds of active volcanoes, some of them erupt continuously. The largest, Pele, produces a plume of sulfur dioxide gas that rises 300 kilometers above the surface. The surface itself is covered in yellow, orange, and red deposits of sulfur, constantly being resurfaced by lava flows. There are essentially no impact craters on Io because the surface gets repaved so fast that craters fill in before they can accumulate. Nobody expected this. The prediction models said Io should be cold and dead. The explanation came quickly once the discovery was made. Io sits in a gravitational tug-of-war between Jupiter and the other large moons. This gravitational flexing, called tidal heating, squeezes Io's interior continuously like a stress ball. The friction generates heat, enormous amounts of heat, enough to keep the entire moon in a state of constant volcanic upheaval. This discovery changed how scientists think about the potential for geological and biological activity in the outer solar system. If tidal heating can power volcanism on Io, it can potentially power liquid water oceans on other moons, far from the sun where solar energy alone cannot do the job. Every ocean moon we talk about today, Europa, Enceladus, Ganymede, traces its significance back to what Voyager found on Io in 1979. Number 11. The rings of Jupiter, the planet nobody expected to have them. Before Voyager 1 arrived, only Saturn was known to have rings. Saturn's rings are spectacular, visible through a backyard telescope. Unmistakable. Jupiter's rings are nothing like that. They are thin, dark, made of microscopic dust particles rather than ice and rock, completely invisible from Earth with the telescopes of the 1970s. Nobody expected Jupiter to have rings. When Voyager 1 was programmed to look for them, it was almost an afterthought, a low-priority observation tacked onto the mission plan because one scientist argued it was worth checking. The rings were there, faint, thin, barely there, but real. Jupiter has a ring system. This discovery immediately raised questions about Uranus and Neptune. If Jupiter had rings, planets whose composition and dynamics nobody fully understood, maybe the other outer planets did too. Voyager 2 confirmed rings around Uranus in 1977 before arriving, and confirmed rings around Neptune during its 1989 flyby. The lesson from Jupiter's rings was fundamental. Ring systems are not rare exotic features of one special planet. They are a natural consequence of moons and debris in the gravitational influence of large planets. Most large planets in the solar system have them. Number 10. The ocean under Europa. The discovery that changed the search for life. Voyager didn't directly detect Europa's subsurface ocean. That confirmation came later from the Galileo spacecraft, but Voyager 1 and 2 provided the first close-up images of Europa that made scientists stop and stare. The surface of Europa is almost perfectly smooth, almost no craters, the smoothest surface of any solid body in the solar system, and it is covered in a network of brown reddish lines, cracks, stretching across the entire moon in complex intersecting patterns. These cracks looked exactly like what you would expect if the surface of ice was floating on liquid water beneath. The surface was not rigid and static. It was moving, shifting, cracking, and refreezing. The implication was staggering. Europa, a moon of Jupiter, might have a liquid water ocean under its ice shell, an ocean that has been liquid for potentially billions of years, an ocean kept liquid by the same tidal heating mechanism powering Io's volcanoes. Europa's ocean is now one of the most promising locations in the solar system for extraterrestrial life. The Europa Clipper spacecraft launched in 2024 and is currently en route to study it in detail. All of that started with Voyager's images of a cracked, smooth ice shell that nobody expected. Number 9. Titan's thick atmosphere. A moon with weather. Before Voyager, scientists knew Titan had some kind of atmosphere. What they did not know was how substantial it was. When Voyager 1 flew past Titan in 1980, it found an atmosphere so thick and opaque that the surface was completely invisible. Not thin wisps of gas, a dense orange, smoggy blanket of nitrogen and complex organic chemicals, thicker in atmospheric pressure than Earth's own atmosphere. This was extraordinary. Titan is the only moon in the solar system with a dense atmosphere, and the chemistry of that atmosphere, nitrogen with organic molecules including methane, resembled what scientists believe the early Earth looked like before life emerged. Voyager couldn't see through the haze to the surface. That would take Cassini and the Huygens probe landing in 2005 to reveal the lakes of liquid methane, the river channels carved by methane rain, and the hydrocarbon sand dunes. But Voyager set the stage. It told us Titan was not a dead frozen rock. It was a world with chemistry, with weather, with a complex active atmosphere doing things we had no framework to understand. Number 8. The volcanic plumes of Triton, a moon going the wrong way. Triton is Neptune's largest moon, and it is deeply strange for two reasons. First, it orbits Neptune backwards. Every other large moon in the solar system orbits in the same direction as its planet rotates. Triton goes the other way. This means it was not formed with Neptune. It was captured, a Kuiper Belt object pulled into Neptune's gravitational influence at some point in the ancient past. Second, when Voyager 2 flew past Neptune in 1989, it found that Triton has active geysers. Not volcanic geysers, nitrogen geysers, columns of nitrogen gas erupting from the surface and rising several kilometers into the thin atmosphere on a moon where the surface temperature is minus 235 degrees Celsius, the coldest surface temperature of any measured body Voyager visited. The mechanism appears to be solar-powered, despite Triton's enormous distance from the Sun. Sunlight penetrates Triton's transparent nitrogen ice surface and heats darker material below. The trapped gas eventually builds enough pressure to erupt. Active geology on a captured retrograde moon at the edge of the solar system, at temperatures cold enough to freeze nitrogen solid. Nobody expected any of that. Number 7. The complexity of Saturn's rings. Not rings, a system. Before Voyager, scientists knew Saturn had rings. They thought those rings were relatively simple, a few broad bands of material and stable orbits. Voyager destroyed that picture completely. Saturn's rings are not simple bands. They're a system of extraordinary complexity. Thousands of individual ringlets, gaps within gaps, spiral density waves propagating through the ring material like ripples. Braided rings that twist around each other in ways that should be dynamically impossible. Spokes, dark radial features rotating with the rings, but moving at the wrong speed for their orbital position, appearing and disappearing on timescales of hours. The spokes alone consumed months of scientific debate. Nothing in classical orbital mechanics explains features that rotate with the rings, rather than with Keplerian velocity. The current explanation involves electromagnetic effects from Saturn's magnetic field, but it took years to develop that understanding. Shepherd moons, tiny moons whose gravity maintains the sharp edges of certain ring gaps, were predicted theoretically and then found exactly where the math said they should be. That was one of the first predictive confirmations of a specific theoretical model by Voyager data. The rings turned out to be not a static structure, but a dynamic, constantly evolving system that would take decades of continued study to partially understand. Number 6. The scale of Jupiter's magnetosphere, the largest structure in the solar system.
Jupiter has a magnetic field. Scientists knew that before Voyager. What they did not appreciate was the sheer scale of it. Jupiter's magnetosphere, the region of space dominated by its magnetic field, extends roughly 7 million kilometers toward the Sun and trails behind Jupiter for hundreds of millions of kilometers, past the orbit of Saturn. If you could see Jupiter's magnetosphere with your eyes from Earth, it would appear larger in the sky than the full moon, despite being 600 million kilometers away. Voyager measured radiation levels inside Jupiter's magnetosphere that would deliver a lethal dose to an unshielded human in a matter of minutes. The spacecraft instruments themselves were damaged by the radiation, despite being specifically hardened against it. Io, sitting inside this magnetosphere, acts as a source of ions. The volcanic eruptions inject sulfur and oxygen ions into the magnetosphere, creating a plasma torus, a donut-shaped ring of charged particles surrounding Jupiter at Io's orbital distance. Voyager detected this plasma torus, and it turned out to be one of the most energetic particle environments in the solar system outside the Sun itself.
Number 5. The Interstellar Medium. What space actually is between the stars. The ultimate discovery, the one nobody could have fully predicted because nobody had ever been there before. Voyager 1 crossed the heliopause, the boundary where the Sun's solar wind gives way to the interstellar medium, in August 2012. Voyager 2 crossed it in November 2018. What they found challenged existing models significantly. The density of the interstellar medium was higher than expected. The magnetic field direction was different from predictions. The boundary itself, the heliopause, was sharper and more defined than models suggested, and after crossing it, Voyager 1 detected that the interstellar medium was permeated by plasma waves, oscillations in the charged particle environment that allowed scientists to directly measure the electron density of interstellar space for the first time. The electron density measurement was a genuinely new kind of data. We had never directly sampled interstellar space before. Everything before was inference from observations made from within the solar system. Voyager 1 is now more than 24 billion kilometers from the Sun as of 2026, still transmitting, still returning data. Its signal takes over 22 hours to reach Earth, traveling at the speed of light. A spacecraft launched in 1977 with less computing power than a modern calculator is our only direct sensor in interstellar space, and it is still working.
Number 4. The Great Red Spot up close. A storm older than science itself. Scientists knew the Great Red Spot existed before Voyager. It had been observed through telescopes since the 17th century. But seeing it from a distance and seeing it up close are completely different things. Voyager revealed the internal structure of the Great Red Spot in detail for the first time. The storm system is not a simple rotation. It is a complex, nested system of counter-rotating cells. Smaller storms shown being absorbed by the Great Red Spot as they drift into it. The edges of the storm rotating faster than the interior. Complex, turbulent wake structures trailing behind it. The Great Red Spot at the time of Voyager's flyby was roughly 25,000 kilometers across, larger than Earth. It has been shrinking since. It is now significantly smaller than when Voyager observed it, but it has been a continuous storm for at least 350 years of human observation, and possibly much longer. What powers it? How it maintains coherence for centuries? Why it is red? All of these questions were sharpened by Voyager's observations, and none of them are fully answered even now. Number 3. The Pale Blue Dot. The photo that changed how we see ourselves. On February 14, 1990, Voyager 1 turned its camera backward at the request of Carl Sagan and took a photograph of the solar system from a distance of 6 billion kilometers. Earth appears in that photograph as a single pixel, a pale blue dot, less than a 1/12 of a pixel in size, caught in a scattered ray of sunlight. Carl Sagan wrote about this image in terms that have never been improved upon. Every human who ever lived, every king and peasant, every act of creation and destruction in history, every civilization, on that dot. This was not a scientific discovery in the traditional sense. It was a perceptual shift, the kind that happens once in a generation if you are lucky. The pale blue dot photograph has been reproduced more than almost any other image in the history of astronomy. It changed how a generation of scientists thought about the significance of Earth and the importance of protecting it. That came from a spacecraft that was already 13 years into its journey, running on dwindling power, turning around one last time to look back. Number 2. The sounds of space. Plasma waves that become music. Space is a vacuum. Sound cannot travel through it. This is a fact. But Voyager's instruments detected something that, when converted to audio frequencies, produces something that sounds startlingly like sound. Plasma waves, oscillations in charged particle environments, were detected throughout the outer solar system by Voyager. NASA scientists converted these frequencies into audio, and what came out was extraordinary. The sounds of Jupiter's magnetosphere, a deep, roaring cacophony of electromagnetic noise. The sounds of Saturn's rings, a complex rhythmic pattern of wave interactions. The sound of Voyager crossing the heliopause, a sudden shift in the plasma environment captured as a distinct change in audio character. These are not sounds in the traditional sense. They are electromagnetic phenomena translated into audio by scientists to make them perceptible to human senses. But they reveal something profound. The outer solar system is not silent. It is filled with complex wave phenomena that carry information about the environments they travel through. The recordings are available and genuinely haunting, worth looking up after this video. Number 1, that it still works. The most unexpected thing of all. Here is the most unexpected thing Voyager found. Not a moon, not a ring, not a magnetic field. The most unexpected thing is that after 49 years, launched in 1977, now in 2026, both spacecraft are still operating. Voyager 1 and Voyager 2 were designed for a 4-year mission to Jupiter and Saturn. That was the plan. 4 years, done. Instead, they kept going. The mission was extended to Uranus and Neptune, then extended again into the Interstellar mission. The spacecraft have now been operating for longer than many of the scientists who built them have been alive. Their power comes from radioisotope thermoelectric generators, RTGs, converting the heat from plutonium-238 decay into electricity. That power is declining at roughly 4 watts per year. NASA has been systematically shutting down instruments to preserve power for the most critical ones. In 2023, Voyager 1 began sending garbled data back, a corrupted memory chip in the flight data system. Engineers spent 5 months troubleshooting a spacecraft 24 billion kilometers away with a 45-hour round-trip communication delay. They fixed it by sending commands to route around the damaged chip. They fixed a 49-year-old spacecraft in interstellar space using software patches. The Voyager spacecraft will run out of power sometime in the late 2020s. When they go silent, they will continue drifting outward forever, carrying the golden record with greetings in 55 languages, music from around the world, and instructions for finding Earth. In 40,000 years, Voyager 1 will make a close approach to a star in the constellation Camelopardalis. Whatever is there, if anything, will have the chance to find it. We sent a message to the universe, and it is still traveling. 12 things Voyager found that nobody expected. Volcanoes on a moon of Jupiter, rings around planets that should not have them, an ocean under ice, a captured moon erupting geysers in the cold, a storm older than modern science, a photograph that changed how we see ourselves, and a spacecraft that refuses to stop working. Voyager was supposed to last 4 years. It lasted a civilization. Subscribe to Cosmic Hives. See you in the next one.